Now that we've set up the generalities for doing hypothesis testing, we're going to look at how to do it with various population parameters. And we're going to start with a sample mean and making claims about the population mean. And we have two possibilities. We know the population standard deviation, sigma, or we don't. We're going to start off with, in this section, that we know what the population standard deviation is. So, we have some requirements for testing these claims. The sample is a simple random sample. The value of the population standard deviation, sigma, is known. And either the population is normally distributed or n is greater than 30. Since we are doing mean, knowing sigma, there is our test statistic. It's a z-score, so we're going to use table 4 to find p-values or critical values. Z equals x bar, the mean of the sample, subtract the population mean divided by the standard deviation divided by the square root of the sample size. Okay, now there are 3 methods of doing hypothesis testing. And they're very, very similar, but they have some slight differences, and that's what we're going to focus on. So first, we're going to focus on just the p-value method. And basically, there are 8 steps to doing a p-value method type hypothesis test. Okay? These are not necessarily doing 8 different calculations. Most of it is just like setting up what is it you know in the problem. So, step 1, what is the symbolic form of the claim? That's something like, hey, mu is greater than, mu again because we're doing the mean. 2, what is the symbolic form of the claim is false? The counterclaim, it'll be the opposite of whatever the claim is. Remember that H1 does not contain the equal sign, H0 does contain the equal sign. H1 could be a not equal to, but H0 will always contain the equal sign. We have to select our alpha. Now it says select alpha, but truthfully the problem is going to give us alpha. We have to identify the relevant statistic in determining the sampling distribution. Basically that's like, in this case, we're going to use table 4. That's really the purpose of that part. Whereas if we do not know sigma, if we do not know the population standard deviation, then we have to use table 5, which are t-scores. And if we're doing standard deviation and variance, then we use table 6, which is the chi-squared table scores. Now, 1 through 5 really are just identifying things. It's not until step 6 that we actually do any kind of calculation. Here we're going to find the test statistic and then find the p-value from that test statistic. So this is really where our calculations come in, step 6. Step 7 is where we actually make our judgment. Okay, we reject the null hypothesis, we reject H0 if the p-value is less than alpha, or we fail to reject if the p-value is greater than alpha. And the best way to think about this is, alpha represents an area in the tail, or in both tails. If the p-value is less than that, its area is even more extreme than alpha's was. Alpha actually extends a little bit more towards the middle than the p-value area does. On the other hand, if the p-value is bigger than alpha, then its area extends a little bit further towards the middle than alpha does, and therefore we would reject the null hypothesis. And then step 8 is basically, all right, now that we're done, now that we know whether to reject or fail to reject, we restate our results in terms of the claim. We address the claim. And generally it's going to take 1 of 2 forms. Either there is sufficient evidence to support the claim, or there is not sufficient evidence to support the claim. Alright, in the traditional method, the beginning part, 1 through 5, is all the same as doing the p-value method. In the p-value method, we found the test statistic and then found the p-value from it. In the traditional method, we still find the test statistic, just like we did up here, but we're also going to find the critical values and the critical region. Then, just like up here, we get to our comparison step. We reject H0 if the test statistic is in the critical region. And we'll show you an example of that in just a moment. We will fail to reject H0 if the test statistic is not in that critical region. And then just like 8, we're going to restate the result in simple terms. And then finally, while this is not given to you in the section, there is the confidence interval method. Basically, you build a confidence interval, and we did that in an earlier chapter. The beginning part's all the same. We're still going to do the symbolic form of the claim. We're still going to make our hypotheses. We have to figure out, is it two-tailed or one-tailed? We want to construct a confidence interval with a confidence level based on alpha. And if it's one-tailed, it's 1 minus 2 alpha. If it's two-tailed, it's 1 minus alpha. And unlike anything we had to do up above, since we're doing a confidence interval, we need a margin of error. And so we're going to have to find out what the margin of error is. So again, in step 6, we will build our confidence interval. In this case, x bar subtract the margin of error, x bar plus the margin of error. Mu is estimated to be within that confidence interval. And basically, here's how it works. We reject the claim if the parameter is not included in the confidence interval. In other words, it's outside of this range that we say is the most likely for mu to be in. Or the opposite, if it does fall within the confidence interval, then we fail to reject because anything in that confidence interval is what we expect anyway. So if it's falling within that, it says basically that we can't throw out the null hypothesis. And then finally we restate in simple terms. So let us look at, we're going to look at one problem, but we're going to look at the same the various steps and how they differ depending on what method we want to do, so that I can emphasize what's different about each one. So here's our problem. We have a sample of weights of 40 men, has a mean of 172.55 pounds. So again, that's the mean of the 40 men. That's our sample mean. Research from other sources says that the population standard deviation of men's weights is 26 pounds. So there's our sigma for the population. Use these results to test the claim that men have a mean weight greater than 166.3 pounds. So, please note, we got that in a sample, and here's our claim, of which this is definitely bigger than that. But really what we're trying to test is, does that allow us to have the evidence that supports this claim? We're going to use an alpha 0.05. As I said, it's usually going to give you the alpha. Sometimes it gives you the confidence level, and then you have to subtract from 1 to get your alpha. But usually it'll give you the alpha. So, first off, are the minimum requirements met? It's a simple random sample. It tells us that. It tells us a sigma, so we do have a sigma is known, 26 pounds. And n is bigger than 30, and it's 40 in this case. So we're going to start off with, let's look over the p-value method first. So, state your claim. Okay, again, the claim was that men have a mean greater than 166, greater than, so mu is greater than 166.3. Counterclaim, notice how it's the opposite, that was greater than, so this is less than or equal to. Step 3, what are the null and alternative hypotheses? So here's the null, it always gets the equal sign. And here's the H1, and notice that H1 matches the claim. Normally, with greater than or less than, it will match the claim. Alpha is 0.05. Remember, in 5, we want the sampling distribution. We're going to use table 4 because we're looking at mean when we know sigma. Step 6, now we figure out our test statistic. So 172, that's from the sample. 166.3, notice that's from the claim. 26 over the square root of 40, we get a 1.52. The p-value will be to the right because of the greater than. The p-value will be to the right of z equals 1.52. So what area is that? Well, if z is 1.52, table 4 tells us the area is 0.9357, but that's to the left. The table always works to the left. So if we subtract from 1, we get 0.0643. That's the area to the right, so that's our p-value. So again, the p-value is going to match that area to, in this case, to the right, because we were looking at the greater than case. So that's it. Those are our calculations. Now, make our comparison. Step 7. Since the p-value at 0.06 is greater than alpha at 0.05, we fail to reject the null hypothesis. The null hypothesis was mu equals 1.66.3. Okay? It could be. We can't reject that because our p-value was greater. Our p-value actually extended further in to the distribution than alpha did. And so, even though x bar equals 172.55 is greater than 166.3, it's not extreme enough to be unlikely. Could be just chance that it was that high. And that's one of the things you have to understand about the whole idea about probability and inferential statistics. Okay, it doesn't prove things. It looks at likely or unlikely. You know, if you flip a coin 10 times, most of the time you're going to get 5 heads, 5 tails, 6 heads, 4 tails, 7 tails, 3 heads, something like that. Very rarely will you get 10 out of 10, but you will occasionally. The real question is, when you get a value that's off of your average, is it off far enough to suggest that you can support the claim that it should have been higher? In this case, 172.55 is higher than 166.3, but it's not extreme enough to be unlikely. It could have been just random chance from one sample to the next. Alright, now let's look at the traditional method. And you're going to see, you know, there's a lot of similarities. So, steps 1 through 5 are the same. We're figuring out our test statistic again, just like we did up here. Same 1.52. None of that's going to change. Now, up here, once we had the 1.52, we then turned around and found our p-value based on that z-score. Down here, now that I have the 1.52, I turn around and look at alpha and say what z-score should go with that particular alpha. Well, it's 0.05 to the right. Remember, the table only goes to the left, so we have to subtract from 1. So this is what we actually look up in the table. And it turns out a 0.95 gives us a 1.645. So this is our critical value based on alpha. This is the test statistic. This is the critical value. If I change alpha, that will change. This one's not going to change unless I do a different sample. Now, since the 1.52 is less than the 1.645, and please note, a z-score of 0, that's the mean. So the smaller this gets compared to that, the closer it is to the middle. The closer it is to middle, the more likely it is to happen. So the fact that this is true and it's not in the critical region, which means it's not bigger than 1.645. It's not further extreme from the middle. We fail to reject the null hypothesis of H0 equals 166.3 pounds. Again, 1.52 is closer to the middle than 1.645. In inferential statistics, you are rejecting things that are extreme, that are unlikely. Another way of kind of thinking about this is early on in a much earlier chapter, we talked about, what do we expect? Well, we expect 95% of the data falls within 2 standard deviations. That's less than 2 standard deviations. So from that standpoint as well, we should not be surprised to get a value like 1.52. So again, even though x bar equals 172.55 is greater than the 166.3, it's not extreme enough to be unlikely. Could be just chance that it was that high. The results between the p-value and the traditional method or rejection region method should give you the same answer. In the p-value, you are comparing the p-value area to alpha, which is an area in the tail. In the rejection region method, you are comparing 2 different z-scores. You are comparing the z-score you got from the test statistic with the z-score, the ZC if you would, the critical value z-score that you got from alpha. Now, finally, a little short bit about what if you did confidence interval instead. Again, steps 1 to 5 aren't really any different. However, your step 6 is totally different because now we got to build our confidence interval. So, we have a right tail test because of the greater than. Our alpha is 0.05, so that means that's 0.05 in the right tail. If we, again, since it's right tail, we have to subtract from 1, which gives us 0.95 to the left. The z-score for that is 1.645. And by the way, notice how those two match. They've got to be the same thing because you're really talking about the same critical value. This refers to a 90% confidence level, okay, because basically it's 1 minus 2 alpha for 1 tail. Now we can find our margin of error, which is the critical z-score, times sigma over the square root of n. Plug those in, we get the margin of error is 6.76. So our confidence interval will be x bar minus e and x bar plus e. Plug in our numbers. Again, that's the x bar, that's the e. And we have now built in step 6. So all of this stuff, that was just step 6. We build our confidence interval. It's from 165.79 up to 179.31. So values in there are what we expect. Now, 166.3 is in there. In fact, there are also values a little bit less than 166.3 are in there. So because of that, we can't reject the idea that H0 is just 166.3. We do not have sufficient evidence to support the claim that it has to be greater than 166.3. Again, the 172.55 is more than 166.3, but it's not extreme enough that it makes us doubt whether the claim is true or not. So, that's an example. Most of the homework problems look to be p-value types, where you find the test statistic and then you use that to find the p-value. There are a few that will be the traditional, I didn't see any of the homework problems that would be the confidence interval, but since we spent a lot of energy in the last chapter making confidence intervals, I thought you should look at that method for evaluating a claim. And so that is it for section 2.